morning. Let's see where we are. So maybe let me apologize for changing title. I mean, it was partly intentional because I didn't know who will come, so I just gave tentative title that could be then refined to to anything. Changes because yesterday people, some people came after and said, what exactly are you working on now? I mean, don't tell us about what you worked on in the last millennium, but tell us about what you work on right now. And so that's partly the reason. Also, just looking at listening to questions, I thought maybe this will be more appropriate than what I thought about initially. Also, can I ask just two questions, just to calibrate myself against the audience? How many people here are undergraduates versus graduates? Okay, and undergraduates, right? And then how many people here came today but didn't come yesterday? Because then maybe I should repeat what I said yesterday at the end for those people. Because so yesterday there was somehow a discussion at the end about education issues and something like that, and maybe it caused some questions, and people came and asked, and so maybe we should do it again today. We'll see. So great. Okay, good. So let's start with graphene. Graphene is a big subject, and because there will be one more talk about graphene, I will have to do a little bit of introduction, also to explain you what graphene is about. I apologize for this color that's wasn't supposed to be like that. Some computer glitch or projector glitch. I'm not sure. It looks perfect over there. So graphene now is, it grew into a big field studying 2D materials, which are two-dimensional. And so there is a large family of 2D materials which can be isolated, down to a single atomic layer or two atomic layers like graphene, and its relative or nitride that look like a chicken wire, two-dimensional atomically thin chicken wire layer, and then there are various other atomically thin materials of different kinds. They can have different electronic properties. They can be conductors or insulators, or nitride is a wide gap insulator. These materials can be medium gap, can be semiconductors, medium gap or narrow gap. There are superconducting materials with charge density wave, and then topological materials. So there are materials with all different electronic properties. All can be made one layer thin. And so there is a big field of studying these materials. A reason people are interested is that these materials have some interesting properties that are listed here. They're atomically thin, transparent, flexible, optically active. They have a wide broadband absorption. They have states which are exposed. You can act on them by proximal gates and change their properties, their high mobility. And so these material properties, they manifest themselves in a variety of physical properties. And so there is wide range of people who are either exploiting these properties to build some useful devices, or trying to use the physical effects that follow from these properties to do some interesting physics. So there are at least two directions: trying to do some physics and then trying to build devices. And maybe just to as a quick introduction, something probably maybe Pilkatine, the mother of all these two-dimensional materials, graphene, is a carbon monolayer with this structure, and from a crystallography point of view, it has a two-atom unit cell, because two carbon atoms that are marked red and blue, they are not equivalent under translations. They are equivalent under translations combined with kind of 80-degree rotation, and because of that, because of that, the band structure has two branches, and because of that symmetry, rotation, and translation, these two branches have connection which is protected. They touch, and this connection cannot be, the points where they touch cannot be easily removed by any perturbation that agrees with the symmetry. And this is a result of low energy band structure near these points where the two bands touch, being of this form. If you zoom in and linearize, so that then we get near these points we get behavior similar to massless Dirac fermions, where fermion wave function is two components corresponding to wave function amplitudes on the blue side and the red side, and the Hamiltonian that describes it is a 2 by 2 matrix Hamiltonian, where two spin components correspond, they're not spin, they're pseudo-spin in the literature, and they correspond to wave function amplitudes on the two sides. So, it's an interesting material where the spatial wave function mimics spin in the Dirac equation, and this is more or less an exact mapping. One can use this transformation to write down a Hamiltonian for low energy states that will look like massless Dirac Hamiltonian with a two-component spinner in the literature, called Chirality spinner, and one can add electromagnetic fields, and in the canonical way, long derivative to couple to magnetic field, and adding scalar electrical potential, and so this model will describe everything that happens in graphene with conduction electrons near the Dirac wave. And in this approximation, there is no coupling between Dirac fermions here and Dirac fermions here. They're independent species, and some coupling appears at high orders perturbation, but zero approximation is just two decoupled Valley species that each of them behave like massless Dirac particles. Okay, so yeah, I realize that probably this is too fast for some people, and also useless for other people because they know all about it. So please, stop me and ask questions when you want to clarify something, because then otherwise we'll lose people too early. We don't want to lose anyone too early. We want to lose everyone eventually, but not too early. Yeah. So graphene is the mother of two-dimensional materials, and of course, it got two mothers, or maybe better to say fathers, which are pictured here, and to whom we owe the excitement of studying graphene. So with that, let me see. Yeah, so the massless Dirac Hamiltonian defines graphene as a model relativistic quantum mechanics system, and one can see that there are very specific properties that are derived from massless relativistic character of electrons in graphene. In particular, this linear dispersion relation that we saw over here near the Dirac points, as they're called, it makes electron dispersion, energy versus momentum, very steep, and that allows electron properties to be gate tunable over a very wide range, because energy versus momentum varies very steeply. You can vary carrier density by applying a gate potential in the range of a few volts, and so that's much higher than in any other known material. Usually gate voltage variation is at least 10 times smaller than a typical semiconductor. So there's a wide gate voltage range. That's pretty useful. And that wide gate voltage range translates into a wide range in which you can vary the chemical potential. So you can vary the Fermi energy in graphene. You can vary the Fermi energy in graphene by tuning voltage on gate, on the gate over a range of a volt. And that's unprecedented because all other semiconductors have a number which is much lower, and it makes graphene very interesting from point of view of optics, because you can vary it over, vary your Fermi energy over the energy of which is the energy of a photon, and you can block or allow optical transitions by acting with voltage on the gate. So that's something which is widely explored now in building devices. And likewise, another property which is derived from relativistic Hamiltonian is the chirality, the fact that, as you can see by staring at this Hamiltonian, spin orientation is locked to velocity, and because of that, carriers propagating one way have their spin, pseudospin, aligned along the velocity, and so that has implications for scattering. It suppresses back scattering, makes material immune to disorder, and ultimately that explains why electronic properties are so much better than one would expect in an atomically thin material, which is exposed to all kind of environmental perturbations, disorder, etc. And so high mobility of graphene is in fact due to that chirality effect, which is relativistic in its origin, right? And so these two effects, they are well understood and they're widely explored in devices. There are various devices, maybe we'll leave it for questions, that rely on what I just said. But then there are also other properties which are also relativistic in their origin, haven't yet found their way into engineering. In particular, there are interesting effects due to Berry phase in these materials, and so that's what we'll talk about today. Also, if you think about electron-electron interactions, graphene is an example or model system where you have quantum electrodynamics type of phenomena at strong coupling, and so that leads to many interesting physical effects and is under intense investigation by physicists and not yet by practical people. Right. So yeah. So I think sorry for this blue background. So right. So what I would like to do today is to focus on the valley degree of freedom and how we create topological currents in the valley degree of freedom that transmit transmit valley variable, and we'll be using in particular the fact that electronic states in graphene are exposed, and so you can put in something nearby and alter electronic structure to make it suitable for valley transport. And so we'll focus on that small subspace, and with that I proceed to my main part of my talk. Maybe I should stop and ask if there are questions about general things.
What's topological current?
What's topological current?
Right, that will come. Yeah.
What's with spin?
The ordinary spin. The regular spin. So
yes.
the regular spin is always there. It does not couple to Dirac pseudospin because spin orbit is very small. Carbon is a light atom. It has small atomic weight because of that spin orbit, and this atom is very small. Also, when you make this graphene structure, every atom has a very symmetric environment, and that suppresses spin orbit coupling even further. So spin orbit coupling in a band structure, graphene band structure, is very, very small. So the real spin is just nearly completely decoupled from orbital motion, and it makes it kind of boring from some point of view. But also, there are people who like it because if you want to observe long spin lifetime, then graphene is a good material. You can inject spin and see that spin polarized electrons can diffuse around over long distances without spin flipping. And so some people like graphene because of that and use it to realize long range spin transfer. But that's precisely because spin doesn't show up in the Hamiltonian. Yeah?
We're talking about electron spin or nuclear spin?
Electric or what?
Electron spin or nuclear spin?
Oh, electron, yeah. Nuclear, right, there is carbon 13 and carbon 12, right? So one has nuclear spin and one doesn't. There is in principle a possibility to make graphene with, in which every atom has nuclear spin. I don't know if people looked into it yet. Maybe not. I mean, it's interesting, but I mean, people have done some of that with carbon nanotubes. There are carbon nanotubes where all carbons are spinful, and then they have some interesting properties, but I don't know if anyone did it with graphene yet. But anyway, so the question was about electron spin, and we're not going to, even electron spin is not going to come up. Yeah. Yeah.
This is pseudo-spin velocity locking effect on scattering. I actually didn't know about it, and the question, will it be the same as a topological insulator?
Mm-hmm. Yeah.
I mean,
exactly.
It's not distinguishable.
So it's distinguishable in the sense that here there are two valleys, and everything will be identical to topological insulator as long as there is no inter-valley scattering. But if there is inter-valley scattering, then it will become a different story. I mean, usually it's a weak effect, but present to some extent, and so it may make a difference. So.
Yes. The question is the following. This expression for the Hamiltonian, can that be derived analytically or
yes.
through
Yes.
formulas
So
from first principle Hamiltonian?
Yeah, yes.
This
So
is
this
just
is
a parameterized description of the numerical solution for the band structure.
well, you can do both. So you can do ab initio calculation and compute all bands in graphene, and then see that near. Yeah, I mean, we should have this discussion in principle, but it will eat up into the rest of the talk. But I mean, you can do a full analysis starting with carbon 4 electrons in the outer shell, and then how they hybridize with each other, and then, as you know, it forms an sp2 configuration with 3 electron orbitals hybridizing with 3 carbon neighbors, and sitting in plane, and then the 4th orbital sticking out and forming an H-shaped orbital perpendicular to carbon plane. So the configuration is not like in a diamond sp3, but like it's a lower symmetry sp2. And then if you start with that as an approximation, then you can show that first 3 electrons are too far from the Fermi level, and their orbitals basically don't matter. So the one that matters is H-shaped one, and then one can do more analysis on this H-shaped orbital and show that they after you treat them, they lead to this precisely this band structure, and it will be half field. So the Fermi level, just from counting number of electrons, will be sitting exactly in the middle. So in pristine graphene, which is undoped, the Fermi level will be right here. So we'll have all Dirac antiparticle states filled and particle states empty. So that follows from either kind of analysis, ab initio or that chemistry type, and one can do it. Will take more time. Yeah, sorry.
So this equation, Hamiltonian, has one constant. This speed, if I recall correctly, is growth speed. What order of magnitude is it for real material?
This one?
Yes.
Yes, so it's 10 to the, oh, sorry, yeah, so I have it. So it's about speed of light divided by 300, so it's 10 to the 6 meters per second, which is typical for any solid. Another way to remember it is E squared divided by h, electron charge divided by Planck's constant is 10 to the 6 meters per second, close to that. And it's velocity unit typical for solid. Okay, so let's move on. Right, so what we want to do is exploit the fact that graphene got several values and use that to create to study transport phenomena where we create currents that flow in the opposite direction, currents for species in each valley that flow in opposite direction, one valley relative to the other valley. These currents will not transmit charge, they will only transmit valley index, and they will tend to lead to valley imbalance in space. Carriers in one valley flow right, carriers in the other valley flow left. There's no net charge flowing through space. And so these currents, because they're charge neutral, they're interesting. They can be long range because they don't lead to any charge buildup or electric field buildup. And but they're carrying something. They're carrying some degree of freedom, so in principle can be used to, encode information, and there are many proposals of that. And so in graphene there are specific tricks that one can use relying on Berry phase to realize valley currents. And so this shows basically the idea. If you think about graphene band, you realize that you can equip graphene band fairly easily with Berry's curvature, and we'll see what's that in a moment. And if you have Berry's curvature, Berry's phase and Berry's curvature, then there is an interesting change of equations of motion of particles. There is an additional term. But if you forget about this additional term, what you see here is the ordinary group velocity equation, saying that velocity is just the group velocity of carriers derived from their energy versus momentum relation. So that's what we always write. And then for momentum, so that's for position time derivative. And for momentum time derivative, we write the usual Lorentz force equation. But turns out that with Berry's curvature, this system is incomplete, and you get additional term which looks like Lorentz force term, but it's in momentum space, not in position space. And in a sense, after you add it, the pair of equations becomes more symmetric. The equation for position times velocity in position space and velocity in momentum space become, look very much.
What physically is omega? What this omega is physically?
It's Berry's curvature. It's a flux. It's a flux of Berry's field. Just wait till we'll talk about that. But if we manage to achieve that, then what we can do is to have something like a Hall effect, but without external magnetic field, which will be controlled by Berry's curvature. And Berry's curvature is nice because it will be tunable by gates, because you can move your Fermi level up and down, and pick large Berry curvature, not so large Berry curvature, and use that. And also another reason that's nice is that unlike Hall effect, which is of the same sign in both valleys, this one will be of the opposite sign in both valleys, because Berry's curvature will be of the opposite sign in the two valleys. And so using that, we'll be able to realize these valley currents that we wanted, where currents in one valley, currents in the other valley flow in the opposite direction, and you get the charge neutral valley currents. So then we begin to answer Grisha's question so let's recall what Berry's phase is. I don't know how many people saw it in the quantum mechanics class. It is usually part of it, but well, just in case. So Berry's phase appears as part of the discussion in the adiabatic theorem. So adiabatic theorem, derived in 1928 by Gordon Fox, says that quantum mechanical system, which evolves slowly in time, tracks an instantaneous eigenstate of the Hamiltonian if the Hamiltonian is changing in time slowly enough. And this is correct, but as Berry shown in 1983, is incomplete. In fact, there is also a phase effect that is due to this time variation. And it turns out that in this time evolution, the state tracks instantaneous eigenstate, but picks up additional phase that depends on the path the system is taking in configuration space, and can be expressed through something that looks like Aronoff-Bohm phase, but generalized to be not in position space, but in any configuration space. So at this point, K just labels phase space in which parameterizes the function. Whatever you vary, whatever parameter you vary will be called K. And then if your instantaneous eigenstate varies as a function of K, please take derivative and then take the inner product with an eigenstate, and that gives you the Berry's vector potential. And then if you integrate it over a path in configuration space, that gives you Berry's phase. And I mean, it's a fundamental part of quantum mechanics in general and the adiabatic theorem in particular. It's interesting. It's an interesting phase because it's geometric. It doesn't depend on how fast or how slow you move. It only depends on the configuration of the path in the phase space, and it's independent of the change of phase of the wave function. So if you worry about gauge invariance, it's gauge invariant. So it's it basically has all the properties as the Aronoff-Bohm phase. And generalizes it to an arbitrary quantum evolution, right? So that's a one-page summary of Berry's phase. Maybe let me ask a question at this point. How many people have seen this? No. Okay. Shall we derive it? No. Okay.
Maybe explain.
Does anyone? I mean, does anyone even care? No.
We are here. We do care.
You care. Okay. So we started at 11:15, right? Okay. So let's take 1 minute. I have some slides that maybe I can use to quickly feed you on that. Cool. Yeah, so please ask questions, because otherwise, I mean, I don't know where we are with this. So if we want to, prove a diabatic theorem, let's start slowly. What do? We take a time-dependent Hamiltonian, and then for every instant of time, we take a basis of eigenstates. These eigenstates, because the Hamiltonian changes in time, they also change in time. So it will be a rotating basis in the Hilbert space. And we can look for a solution to Schrödinger equation, which is a linear superposition of these instantaneous eigenstates. And then the phase in that evolution we can first write down naively. We can say that at each instant of time we have a spectrum of the Hamiltonian given by a set of energies En. And what we can do is we can write the phase factors which are simply integrals of instantaneous energies over time, which if energies are constant will be a linear time phase factor. If they're not constant, we have to write down an integral over time En of t dt, right? And so one can do analysis in this instantaneous basis, which is orthonormal at every instant of time, and prove a diabatic theorem, right? So this is how it's done. So like we said, we'll seek solution in this form. Each instantaneous eigenstate multiplied by the phase factor, which is energy integrated over time, and then we'll put in some time-varying coefficients, and then we'll put it into the time-dependent Schrödinger equation, and derive an evolution equation for time-varying coefficients. So we first plug it in, then we use orthonormality to project on the nth eigenstate, on the mth eigenstate, and m and n states are orthogonal. They satisfy orthogonality relations. So here, from the left-hand side, we only pick up the term number m, and in the right-hand side we have the whole sum. But in the sum, we have one term where these phase factors, which in general varying rapidly because evolution is slow, and so the time over which energy is integrated is long, and so it gives big phase factors. So the big phase factors, if they cancel, we get a slowly varying term, but if they don't cancel, we get a rapidly varying term. So we want to make this distinction and separate the right-hand side into a slowly varying term and rapidly varying term, and then argue that all the rapidly varying terms don't matter, right? So because they oscillate too quickly, and if we integrate, it will make a much smaller effect than this term. So if we argue that and drop them, then because of fast oscillations, then we'll have a simple first-order differential equation with c dot m equal to cm times some number, and then using orthonormality, you can show that this number is in fact pure imaginary. It's a very simple exercise, and so that means that this first-order time evolution generates a phase factor, which is this integrated over time. Okay, done. Questions? Yeah.
What is En of dt prime? What does it mean?
Right. So the intuition is that before our Hamiltonian was time varying, when Hamiltonian was constant, this was the phase factor with which each eigenstate varied in time, right? You have constant energy, and then each eigenstate will have the phase winding at the rate proportional to its energy. And now energy is varying in time, so you have to basically, generalize its phase winding, but make the rate of phase winding, which is the energy, change in time. So that's what this expression achieves. At every instant of time between 0 and t, this phase is winding at the rate given by the instantaneous energy.
But D1D is T prime.
T prime is the time over the time in the interval between 0 and the final time.
But the energy of T prime, your argument is wrong.
Oh yeah, of course not. Yeah, forget about that. Yeah,
D is
type. Yeah, it's
why is purely imaginary? There's a simple argument why it's purely imaginary.
Yes.
Chirality.
Yeah, just read this. I mean, you're quick. You can do it. Yeah, that's a normality. And basically, because if you have a state that changes in time, the velocity in Hilbert space, the change of the state in time is always orthogonal to the state. As a result, if you take in a product, there will be no real part of it, only imaginary. Yeah, more questions? I mean, let's settle. Yeah.
This division on slow and fast oscillating terms, why it is eligible? What is criteria?
So it's only good when we are, consider a diabatic variation. It's a good question. I have to be more careful here. So this is only good if we consider diabatic variation, and what it means is that the rate with which my Hamiltonian varies is smaller than the scale I get from energy level spacing. So I'm looking at the state number n, and got state n plus 1 and minus 1 above it and below it, and the energy splitting must be large enough compared to h bar over characteristic variation time. I mean, otherwise we cannot discard these rapidly varying terms because they're varying at the same rate with which our Hamiltonian is varying, and there are no separate time scales. All right? Yeah, someone, last poll.
Okay, cool.
Okay. Great. So actually, yeah, so there are similarities between Aaron Bohm phase and Berry phase that are interesting and can be discussed. And some people didn't even believe Aronoff Bohm phase when it was introduced, and it was the same with Berry's phase. But I mean, this is all now settled, and let's not. I mean, it's So how do I start view? Right. So okay. So we are. So now we have our Berry space, and I mean the main point. I mean this duration is not so important after all. The main point is that Berry space is very much like electromagnetic vector potential. It generates a phase for whatever configuration space your system varies in, and it's a non-trivial phase if your system makes a loop. So it's very much like Aronoff-Bohm effect when you have a magnetic flux and your particle goes around it, and it can go around it, staying all the time in the region of physical space where there is no magnetic field. There is only a vector potential, and the curl is zero. But nevertheless, it will pick up a phase factor, and it will lead to observable effects in the absence of magnetic field. So the same way here, the main phase effect is due to loop integral of vector potential, and you can express it, of course, by Stokes theorem through flux of a curl of vector potential through an area with a boundary on your loop, and so you can write this as an area integral of this omega area being this one bordered by the loop, and the loop will be in whatever configuration space you are using. In our case, it will be phase space, momentum space, but in other examples, it can be something else. And so this curl is, in fact, called Berry's curvature. So it's like magnetic field, but for Berry's vector potential. And it will not live in the real space, it will live in whatever configuration space Berry's curvature handles. Right. So there is an example of spin 1/2 particle that maybe, again, something that is part of a standard quantum mechanics course, but just in case, let me say that if you take a system, the simplest system where this can be explored is a spin 1/2 in a time-varying magnetic field, and the Hamiltonian is Zeeman Hamiltonian with spin. So this is now real spin 1/2 particle. Coupled to magnetic field, then if your magnetic field is constant, spin will precess about magnetic field. If magnetic field is time varying, it will precess about time varying magnetic field. But if time variation is slow, it will keep processing about time-varying magnetic field and track it, right? And so that's the classical picture that we can derive from classical E&M torque equation, and it's an agreement with the diabatic theorem. And what Berry's phase adds to it is that in this time evolution there will be an additional phase contribution that will be proportional to the Berry's flux through a loop and configuration space. So in this case, the configuration space is the two-dimensional sphere because our magnetic field can point anywhere in space, and one can do simple analysis and show that there is a simple geometric interpretation of Berry's curvature in this case. It will be simply proportional to the solid angle subtended by the loop. So if I take my magnetic field varying in space, the solid angle which will give Berry's curvature will be the solid angle that I see. If I do it very quickly, then there will be a loop, and this loop will define some solid angle, and Berry's curvature will be exactly 1/2 of that solid angle. And what one can show that the general definition from previous page translates into this geometric solid angle formula. And it's very easy to derive. It's actually the next page of those slides. If anyone is interested, let's discuss it at the end. But the reason I'm saying it is that if we now apply it to graphene electrons, which is described by this massless particle Hamiltonian, then this looks like Zeeman Hamiltonian for pseudospin, of course, not for real spin, which is coupled to some effective magnetic field proportional to aligned with particle momentum. And so if I make momentum vary, if I make my electron go around in momentum space, then there will be a phase that I will pick up, and this phase will be calculated by the solid angle. And in this case, actually, things are a bit special because my system is two-dimensional, and because of that, my momentum is always in plane. And because it's always in plane, the solid angle that I showed will be a 2 pi solid angle, because my momentum, if I go around the Dirac point in some way, my momentum will go around equator plane, and so the solid angle formula will predict 2 pi solid angle divided by 2 will give pi Berry space for Dirac electron. And so that's the let's fast forward it, right? So so one can apply the concept of Berry space to transport of electrons in crystals, and do it carefully for Bloch states, and just using momentum of Bloch states as a parameter, and this leads to many interesting things. Your Bloch bands acquire, Bloch Berry space and Berry's curvature, and that leads to topologically non-trivial effects. They acquire what people call topological Chernin variance, which integrals of Berry's curvature or topological band, and that leads to a whole field of geometry-inspired physics. So we're not going to do any of that. I just mentioned it because it's something that is very active now and constantly being discussed. Maybe the last thing, which is in part of a general type of introduction. So let's suppose we have that Berry's gauge field, and we want to derive equations of motion that I postulated with that additional Lorentz-like term. So how do we do that? There are many ways, but perhaps the simplest one is to do the following. We can write down an effective action for positive particle motion just using the canonical procedure. Take P and X phase space, and then write down the action, which is P times velocity in position space minus the Hamiltonian as a function of p and x, and p and x are treated as independent variables in phase space. And then to that, add terms due to vector potential. So this is the ordinary one due to electromagnetic vector potential, electromagnetic times vector potential times velocity in position space. And if you do that and forget about Berry's part, and then look at the Hamiltonian equation of motion derived from Hamiltonian principle, then you get Lorentz force equations, and it's very easy to generalize to Berry's phase because Berry's phase is the same thing as electromagnetic Aron-Lagrange phase, but in momentum space. So all you need to do is just to put two vector potentials, one that lives in position space, one that lives in momentum space, and gives an effect proportional to a times velocity in momentum space. And if you take that and then put it, still put it in the Lagrange equation of motion or through the Hamiltonian principle, then you have to do a bit of algebra here. But at the end, your equation is just what we said. So if you use this term only, you will get a Lorentz force equation. If you use both of them, you will get Lorentz force in position space and then Berry's Lorentz term in momentum space. Done. Yeah.
We have a hypothesis because Lorentz force is why is the term with dA times d dot? Why it isn't simply p?
Because we are, okay, so let's go maybe a bit back to where we said, so it's this, right? So I have to integrate A inner product with displacement in momentum space, but I can write displacement in momentum space as velocity times dt. So then dk will be k dot times dt, and so that's what we did. Yeah,
so we get an acceleration in Hamiltonian.
No acceleration, no, it's just velocity. But it's velocity multiplied by time difference. So it's really displacement. Infinitesimal displacement. But it's written in this, it's written in this way just to make it look canonical. This is a canonical action. Action written as the time integral of Lagrangian, and Lagrangian is what we see in parentheses. So that's a Lagrangian in the phase space. And if you take our expression for Berry's phase and put it through this, write down displacement, infinitesimal displacement as velocity in momentum space times dt, then you do exactly the same thing for electromagnetic part in position space. Am I answering the right question? No?
Yes, you do, but such things are, in my opinion, better described on a blackboard, and it's hard to follow from slides.
No, I agree, but I mean, what, yeah. Anyway, so I cheated. I must tell you that I cheated a bit here, because when you derive these equations of motion, you derive them for canonical p and canonical x, and to go to physical p and physical x, you have to use long derivative condition and shift p to p prime minus a and x to x prime minus a Berry, but that's standard. So you have to do a bit of algebra in between, and at the end you get the right equations. Lorentz equation is very important to understand various ways, and try deriving it like this, and even if you don't care about Berry's phase, try doing Lorentz equation. It's a lot of fun. Yeah. So we do care about this term. So it's this term that we are going to use now to realize Rayleigh transport, and I only got a few minutes left. So the effect from this term I can understand intuitively as a kind of curveball effect. So when you play tennis, if you spin the ball, it will skew sideways, and that's a general feature of motion of any object that carries vorticity. So you can think about Berry's curvature as vorticity, which is being carried by electron in a solid. And if you're, so in addition to its charge, velocity, position, there is also a vorticity degree of freedom that bears coverage to describe. And it allows you to do just what, just this, make the ball skew sideways, baseball in this case. And I mentioned this classical analogy because it's true for any object carrying vorticity, and it arises, in this case it arises from Magnus effect. In our case it arises from Berry's physics, but anyway. So this contribution to current, by the way, is what's called topological current. Someone asked earlier, but so now we have current or velocity, velocity which has a normal part, which is group velocity, and then also this topological part. So the topological part is what we're going to use, and I mean there is a big field exploring it and using it to study topological effects. Now we are only going here to look at the valley currents, the valley Hall effect, and the task is to convert graphene, which, as we mentioned before, it has Berry's phase, but it doesn't have Berry's curvature because Berry's phase is always pi, no matter what loop you calculated it. So our next question is how to convert graphene into a topological material where you have Berry's curvature. And for that, I think I'm really out of time now. So for that, what you need to do is open up a gap in graphene band structure. And if you open up a gap, and the way to do it is to find a perturbation that produces asymmetry between red side and blue side in graphene lattice that I showed earlier, and this will lead to Dirac mass appearing in graphene spectrum. And as soon as you get a Dirac mass, you get a pocket of Berry's curvature, positive for one band, negative for the other band, near the Dirac point. And one can do calculation and show that in this case solid angle, you get a non-trivial solid angle that will vary as the size of the loop in K-space, so you get a well-defined Berry's curvature. And so the question is, can you do it in graphene and play the curveball? And so this is unfortunately the part which is central for my story, but I only got 1 minute for it. So let me show you collaborators and the final result, basically. So these are students at MIT and experimentalists in Manchester, and collaborator from Exeter University who is sitting right there. And so what you can do, several ways, but the way that we implemented was to put graphene on boron nitride, and boron nitride turns out to be nearly lattice matched with graphene, so it creates a perturbation which distinguishes between red sites and blue sites, and in this way opens up a band gap. This band gap, Dirac mass gap, has been measured, and it turns out to be quite sizable. People see it from activation behavior and transport near the Dirac point, and from activation behavior they infer this value, which turns out to be, real value turns out to be a bit higher, closer to 500 Kelvin, is now confirmed by optical experiments. So it's a narrow band. I mean, in this, when paired with boron nitride, it becomes a narrow band semiconductor with a fairly sizable, gap that allows to do interesting physics, and in particular create Berry's curvature and explore its effects. Then it turns out that there is an interesting dependence on Berry's curvature distribution of whether graphene and boron nitride is axis aligned or axis misaligned. There are different kinds of structures, and they lead to, if you do analysis, it will lead to different kinds of distribution of Berry's curvature in momentum space. But in all cases, you get a pocket of Berry's curvature at the Dirac point. In one case, it's positive, in the other case negative. But you can use it for what we just said, for producing this topological current term in equations of motion, and then inducing valley currents. and controlling them. So people, we're not the first ones doing it, controlling values. It's been done recently using optics. We are doing it using transport, and so let's not discuss optics. So in transport, we want to employ these equations of motion to produce currents which run in opposite directions in different valleys, like we said before, and we want to detect them. So how do we detect them? The way you detect them is, so here, I forgot to say that current that you induce will be transverse to the electric field that you apply. So it will really look like Hall effect, which is what we expect from a curveball, right? Skew sideways. So if you apply a normal electric field, this current will go in the transverse direction. And to detect that, what you do is that you take a long system, a long strip, and attach a pair of contacts here, apply the ordinary electric current over here. This ordinary electric current will create a charge-neutral valley current along the strip. And then this charge-neutral valley current, because it does not produce any field buildup that is when it propagates along, it can flow as far as intervalley relaxation allows it, which in practice means up to 10 microns. It's really far. And so at this remote location, you can put in another pair of contacts, and then there, by a reciprocal of that valley Hall effect, you will get an ordinary electric voltage. So the detection scheme is that you use one pair of contacts to excite it, and then here charge-neutral currents will propagate, and you measure a non-local voltage signal far away. And it's a little bit like, a loose analogy with radio, where you have one charge circuit that excites charge-neutral information carriers, i.e. photons, and then on the other end they are detected by charge circuit again, right? So finally, the experiment. In experiment, there is a long graphene strip with several pairs of contacts, also graphene attached to it, and you can use one of them to apply current and the another pair to detect voltage. And then there is also a backgate by which you can vary chemical potential, Fermi energy through the entire band. And you see spikes in the non-local signal. So the red curve is a non-local signal, and this alignment with local transport measurements indicates that the non-local signal happens exactly when your Fermi energy goes in the region of K-space where you have Barry's pocket, pocket of Barry's curvature, right? So that looks promising. One can do the whole analysis and go consider various details, study possible artifacts and study how it decays with distance. It's observable up to 10 microns in the first experiment. Now I think people see it up to 20 microns in beta samples, and one can go through the whole checklist to make sure that we're not fooling ourselves, and everything is in agreement with theory, all the expectations, and the effect is seen only in aligned devices where you get Barry's curvature, and nothing in non-aligned devices where you don't get Barry's curvature, and it scales as a cube of local resistivity as theory would predict for valley currents. It's pretty good, and maybe I'll skip that. So I think it's a non-local response that is a signature of clear signature of charge-neutral currents couldn't arise because of any charge effects. Charge effects are always confined to near the region near the contacts where you induce current. So that's a good sign. And then there are various questions that this opens up for further investigation. One can try to look at the Chern numbers. One can try to control valley currents better. One can try to detect valley population directly by optical probes, and etc. Right. So I think that's where I'd like to stop and see if there are questions. Yeah.
The symbolic current electron charging neutron, is it enforced by some conservation law or simply something like electrostatic charge neutrality principle? Why does the body current why is it charge neutral?
Well, yeah, so it's because they propagate, in each valley they are good, honest charge currents, but because they propagate in opposite directions in one valley and in the other valley, the net current does not transmit charge.
Why
one
do you
valley
have to cancel exactly?
Good, yeah, so that's a good point. It's because we are doing it without applying magnetic field, so we are time reversal invariant, or we are not, but our material is time reversal invariant, and so there is a time reversal symmetry between valleys, and that enforces the cancellation. Yeah.
So there is different type of pseudoparticles in graphene. There is holes too. So in Hall effect, the effect of holes it cancels out the effect of electrons. How are signs aligned here? How is Berry current of holes differs from Berry current of electrons?
Right. No, that's another good thing to discuss, which I didn't have time for. If you go back to one of those pictures, so if you do analysis, you see that Berry's curvature is of opposite sign for electrons and for holes. This has an interesting consequence, because the sign of the Hall effect then will not, sign of this Berry's Hall effect will be the same for electrons and for holes. For ordinary Hall effect, when you change the sign of carriers, the Hall effect changes sign. Now here you have to change the sign of carriers, go from electrons to holes, but you also change the sign of Berry's curvature, produces the Hall effect. So the result is that the net sign of this Berry's Hall effect, or this valley Hall effect, will be the same for electrons and for holes. And so if you do analysis as a function of carrier density, you predict the same sign of Hall effect for positive carrier density and for negative carrier density for the positional sign change. Yeah.
So how such devices can be used in technology? Can they be used as insulating devices, like, for example, electronic couplers? What is resistance between terminal 1 and terminal 3, if I recall correctly on the diagram?
Yeah, let's not discuss it. I mean, I mean, there are wide-ranging opinions on that. There are people who claim that, well, just like in spintronics, if you create an information transmission by charge-neutral carriers, you can use it for a variety of applications. And then there are, if you try to think more carefully, you find loopholes. I mean, this is under debate. So let's not get into that, because it will be a long discussion. There's another question.
I have a question about the velocity, the formula for the velocity. When we can neglect this second term, and when we cannot neglect this second term in the velocity. The formula for the velocity of electrons in graphene.
You mean this one?
Yes, yes. When we can neglect
so,
this term.
Yeah, I think the answer, honest answer, is that, well, okay, so I could try to hide it, but by saying if you go, the way to hide it is, say if you go to the bottom of the band, where this term is 0, then you'll get dominant contribution from that term. If you don't fine-tune anything, then I think this is small. This is typically small compared to that. What makes it stand out is that it's opposite sign of the two values, and this is the same sign. So you can use this asymmetry to make the dominant effect, because this one will not produce any non-local transport, just the ordinary local transport effect. So here, even though because this term is small, you get something interesting. I think it's small numerically. But well, I have to cannot stop here. If you try to estimate whole conductivity, for example, from this curve and extrapolate to distances where the excitation pair of contacts and the probe pair of contacts are very close, then you will get a voltage, get resistance which is order h over e squared. So this effect becomes of order 1 in these units at short distances.
More questions? Please.
Sorry.
What do you mean effective gating? When I'm speaking about effective gating and empirical, I would, from my opinion, the situation is should be opposite. If you have band gap, you just jump from the upper and down with the small unit of charge carrier density. And here you have continuous.
Yeah, no, that's exactly what my opinion is. When I tell this to my friends, they say, no, you can vary gate voltage continuously, and there is a finite range where you are squarely inside the gap in experiment. So probably it means that there is some disorder in experiment and it creates states inside the gap that I mean, it doesn't occur in theory, but in experiment probably there is some disorder inside the gap that creates a finite region where
I mean the best material for gating is a good insulation.
I know, no, I agree. That's what I always think. In experiment, so for example here in these measurements, you see that there is a finite range where resistivity is very high, and presumably it's because there is something in the gap that some localized states in the gap in the insulating state. So you cannot jump from holes to electrons by infinitesimal voltage. Sorry.
If there are no more urgent questions.
So yes, so let's, I mean, there is this stuff on education, maybe let's do it after.
Okay. So you want to show the same?
No, I mean, we should go on schedule because he'll kill me otherwise.
20 minutes behind the schedule.
No, I'm only 5 minutes behind.
Yeah, you're okay.
I'm good. I'm better than the previous. I'm better than the previous guy.
Yeah.
But I shouldn't be too much behind. So let's do your talk and then talk about everything
Now
else.
we'll have a break.
Okay.
So we continue in 15 minutes, and anyone wants coffee, there is cafeteria downstairs.